And I go with my last problem, of course. So that's the last problem, called as the problem of control. Let's go with exactly what we started off with. So there is a map like this. And this is what my planner tells me. In fact, this is more or less what my planner told me. Now, there are two problems with the plan. The first is no robot can make sharp turns. Can you, while driving, suddenly make a 90-degree turn? Driving would have been so easy. You cannot. So robots cannot make a sharp turn. So the speed is inversely proportional to the square root of the curvature. That's by the centripetal forces and those laws. So this trajectory can never be traced. The second is that there will be noises. The robot will skid a little bit. The motors are not intact. They are sometimes loose, so the robot hovers a little bit. You ask it to go straight, it goes slightly dented on the left. You want to control it at 3 meters per second. It cannot be controlled, and it goes at 3.5 meters per second, which, by the way, is too high a speed for the robot. So you control it at 3 centimeters per second, but it goes at 2.8 centimeters per second. So that's problem. And therefore, that's actually a problem. Now, it was very simple if it would have been a manipulator. So let's first take an example of a manipulator. So I want the manipulator to turn and get into this position. That means theta is its current position. And theta desired is its desired position. The easiest that you can do is that you say, suppose desired position should be reached in delta t time. That means my omega is equal to theta desired minus theta divided by delta t. Just control this. So I mean, it's a fan, it's a regulator. So adjust the regulator as per the speed. And once you adjust the regulator as per the speed omega, you've done. This is typically what's called as the open loop control. This one specifically is problematic because you assume that as soon as you give the command, the motor immediately gets energized and takes omega speed, which is not possible. I ask you to drive at 60 km per hour, you will have to start from 0, then 10, then 20, then 30. Only then you will reach the speed. It also assumes that after reaching theta desired, you will suddenly stop. Not possible. If you're traveling at 100 km per hour, you need time to reduce your speed. But then, of course, I can always make the speed profile as like this. That's not a problem with the open loop control. The problem is that you assume that I can perfectly attain this speed. Now, you actually cannot do that. Not possible to exactly attain this speed, and because this speed cannot be exactly attained, therefore you'll always be traveling with omega plus minus some error, and the error could be extremely large. Sometimes it's not, sometimes it is. So some applications do use open loop control, the errors are not large, but then we're dealing with things where the errors are large. So of course I use the idea, which is measure and rectify errors during motion. And this gives right. And so basically what I need to do over here now is that I'll give it a control signal. That's my robot. Based on the control signal, the robot will move. Now, this may not be exactly what I desired, and because this may not be exactly what I desired, so what I'll do is I'll measure the error. So it's this minus this. And this is what I actually supply as my control. So UT is already written. So that's exactly what I supply as the control. So my control signal keeps on changing as per the error. My control signal keeps changing as per the error. And that's exactly what you've got over here. So I have a manipulator. It starts with, its current position is theta t. And I need it to reach, okay, let's write down the error again. So the example is of a manipulator. The current position is theta t. The desired position is theta desired. The error is theta desired minus theta t, and my control is constant times error. Or ut is equal to kp times theta desired minus theta t. This is what is the P controller. And that's exactly what you do. So you're driving a bike and you want to stop at the garage. So if the garage is long way ahead, so you say that the garage is long way ahead, you travel fast. As soon as the garage is near, closer to you, you brake a little, more close to you, you brake more close to you, you brake more. You are at the garage, you stop. So your speed is proportional to your distance from the goal. Your speed is proportional to the error. Finally, you need to be at the garage when your speed should be 0, and the further away you're from the garage, the higher is your speed. So in case of the manipulator, this is the speed of the motor, or omega t, the angular speed of the motor. That's exactly how it will behave. I've got theta t over here. This is my theta desired. This is suppose theta at time 0. This is where I start off. This is my time. Manipulator example. I'll go at a very high speed because error is large. Now, theoretically, the speed could be very large when error is very large. So if you're making a simulator of your own, ensure that this is limited, because even if you make a fan work at full speed, it doesn't go at infinite speed. It limits it up based on what it really can, and that's same with robots. You cannot make them travel faster than what the actual speed is, or the actual speed is always limited, while this could be extremely large. So I go at a very large speed, then as soon as the error reduces, I reduce my speed, I reduce my speed, I reduce my speed, I reduce my speed. Here the error is 0. The speed becomes 0, but due to noises, I will travel like this. Momentum, I'll travel like this. I'll travel all the way up over here. The thing is that towards the end also I'll be oscillating around over here. This is called as the rise phase, when the time needed to go to 90% of your convergent steady state error. This is called as the overshoot. This is the settling time. The time when you settle down to a steady state error, and this is what is the steady state error. It's not zero, so you revolve around a small value. And you'll keep on continuing going like this. So that's what's a P controller, and that's what drives the manipulator. So you've got a theta for the current. You know the object that you wanted to pick, so you know the pose of the manipulator of the end effector to pick up the object. Inverse kinematics, you know exactly what angles each one of the arms should keep. So every arm gives you a theta desired, and you control every arm independently. That makes you reach a theta desired. Now, very quickly, the little problem over this thing is that sometimes there's a constant error. The motors, there's wind blowing, so even if you travel straight, you will actually go on the left. Luckily, not with the manipulators. There's a constant error because you're using encoders to calculate your own position. How do I get theta t at any point of time? I get it from my localization system, which in case of a manipulator is of course an encoder. Now sometimes this encoder lies, the position is not zero and it's reporting at zero, there's a steady error. Sometimes the encoders are not correctly fixed, sometimes there is a wind blowing, sometimes the steering wheel is slightly tilted for mobile robots and so on and so forth. So the problem is if there are external factors, it leads to non-zero steady state error. This can be identified by area under curve. So positive area under curve, which means what's area under the curve? It is integral of error. This has a zero area under the curve, positive, negative. So my control law basically becomes ut is equal to kp times error, where error is theta So this ensures that there are no steady state errors. So it keeps on pushing the system so that it identifies long-term errors, a positive area under the curve which is not reducing, and it acts a force in the opposite direction so that the long-term error reduces. Now there's another funny thing that you're driving over here. So this is your vehicle and you are driving around over here, and you're driving at a very high speed, and you know that you have to stop here And sometimes you can predict that you'll overshoot, and all you want is some system that they can predict that an overshoot is about to happen and can correct you over here. Same example with this one. You know that you're gonna overshoot, but what's the direction of the error? It's negative, so you need to continue moving forward. You need to continue moving forward. Somebody would have said start slowing down, start slowing down. So you need to anticipate errors, and you need to know that overshoot is about to happen, overshoot is bound to happen, and therefore you must control yourself accordingly. That says it is, the anticipation happens by a derivative. We never actually take the integral. You just keep on summing up the errors, and you never take a derivative. You just take a consecutive difference where et is, of course, given by here. That's what's the PID controller. Quick recap. And that's not what I wanted to teach.